Welcome back to ECE 320A. Homework number 3 is due Tuesday when we see each other again. That should be posted, and it's still in Chapter 11 material. You should be starting to read Chapter 12 if you haven't already completed that, because today what we want to do is introduce Laplace transforms. How many have already completed Math 322? How many are in Math 322? Okay, and how many are not going to take Math 322? What I have to do is get everybody on the same page. So if you've already seen this material, please try to understand it from a different perspective. If you haven't seen it, hopefully this will be enough information for you to appreciate what's going on and what the Laplace transform allows you to do. We will define the Laplace transform. We will look at some examples of computing the Laplace transform of some very basic fundamental signals. Then we will talk about basic properties, homogeneity and superposition. And that then allows you to do a lot with linear time invariant systems in the context of the Laplace transform. We will look at what a particular operation does in the context of a Laplace transform. What happens if you apply a derivative in the time domain? What does that look like in the Laplace transform domain? So now we're going to be working with time domain and frequency domain. And we'll be moving back and forth between those. What this is going to allow us to do, though, is we've already worked in the frequency domain with omegas and sinusoidal steady state. What we want to do is start putting everything together and allowing for transient behavior in addition to steady state behavior. Essentially, if you didn't know it, you were living on the j omega axis up until now. When we step into the Laplace transform, we will be able to walk around the entire complex S-plane, not just the imaginary j omega axis. That's what we will do. When we jump into the frequency domain, that's where we're playing, is in this two-dimensional S that has a real axis, the horizontal axis, and the imaginary axis, the vertical axis. That's our space. And that's where the S variable is defined, and it's also where our transfer functions and transforms will be defined, is in this two-dimensional plane. We will then look at an example of applying the Laplace transform just with the little pieces that we've already done up above via definitions, some examples, and basic properties. We'll be able to apply that to now put this differential equation class, which is, what's the name of the math class here? 254 for differential equations. Now we'll be able to say, oh, we have a way of working with that. Not an app for that, but we do sort of have an app, and the app is Laplace transform. We'll be able to convert that into the frequency domain, and now we'll be able to do algebra instead of differential equations. We'll be able to solve differential equations by simply playing with algebra. But the algebra now is using complex variables, S's. And that's what we want to get into in Chapter 12. Let's then get started. This is now going beyond where you have been. We've started with DC circuit analysis, then we looked at sinusoidal steady state. Now we're going to look at introducing all sorts of different silly waveforms and transient behavior. The Laplace transform will be allowing us to analyze that excuse me, when our systems are linear time invariant, LTI. So let me just say that Laplace transforms The reason we're doing it are they're meant to be a simplifying transformation. And you may want to just keep mumbling that under your breath. This is a simplifying transformation. This is a simplifying transformation. If it seems to be going the other direction. What it's going to allow us to do is this conversion that I had just spoke about. We can convert differential equations and those are in the time domain. What we will do is now convert those time domain differential equations, these equations, well, and it could be integral differential equations, equations that contain integrals, derivatives, etc. All of those we want that are in the time domain, we want to convert those into algebraic equations. In the frequency domain. And I'll be trying to make that point clear by jumping around. I'll say, oh, now we're in the frequency domain. Oh, now we're in the time domain. And you need to get comfortable playing with both domains and understanding how to relate the two and where you are, when you're there, etc. And how to go back and forth. Here's the definition. And this definition is single-sided. By that, we're basically drawing a line in the sand and saying, here is time t equals 0, and we want to look at this for all time, all non-negative time, all time beyond t equals 0. We're not going to be looking at the two-sided Laplace transform in this class. The two-sided goes from minus infinity all the way to plus infinity. We're going to draw the line in the sand and say, here's t equals 0, and now let's move on from there. But what we will do is we want to include all of t equals 0. So what we want to do is start on the left-hand side of 0, and we'll label that left-hand side of 0 as 0 minus. We want to include everything that might be happening right at t equals 0. Here's our definition. The Laplace transform of a function of time f of t, we will refer to that, and the f of t will be lowercase. We will call it capital F of s. And that's now this integral. We will integrate over time. So essentially we are looking at this time function f of t over all time from t equals 0 minus to infinity. We look at it, and we actually are doing something a little bit to that function as we're playing with it. We're actually going to weight that by a complex exponential. And then we'll integrate that. So we are basically multiplying this f of t by some magic expression and then integrating all over all time, and that collapses all of that information down into a function now of this complex variable s. And there is the defining expression for the Laplace transform. We're taking our f of t, and you could see that as a decaying exponential. It could be a unit step. It could be an impulse. It could be a sine wave. It could be a cosine wave. That's our f of t. We now scale that as a function of time, but s is a complex number. So we have a complex exponential that we are weighting this time function with. We weight it over all time, and we integrate that entire element or quantity, and then that actually collapses all of that information down into essentially this function of S. And we'll look at some of those functions. And the notation is I will try to write these scripts L, that's the Laplace transform. If we take the Laplace transform of little f of t, that's going to be defined as capital F of S. Let's look at an example just to get us started. Oh, and the other thing is this class is not entitled that, but your next class is entitled Signals and Systems. You need to be comfortable with playing with signals and systems. Right now we're going to look at the Laplace transform of a signal. And what's a very common signal that you play with? The unit step. It turns on at t equals 0 and it's constant at a value of 1 for all time thereafter. Let's then look at what this unit step does when we Laplace transform it. Here's our example. And we'll call that u of t. This is the unit step. That turns on at t equals 0. Actually, it turns on, well, we will be just to the left of when it turns on when we say t at 0 minus. But that's right where it's at. And now we want, and this is a signal, so we are Laplace transforming this signal. That's our goal. We want to know what does that time domain waveform do in the frequency domain? What does it look like as a function of S? If we use our notation, we now are going to say we want the Laplace transform of little u of t. And by definition of that, that's now this capital U of S, which is, by definition, this integral from t equals 0 minus up to infinity of the function of time, u of t, scaled by this complex exponential, or weighted by this complex exponential, e to the minus st, and we want to integrate that with respect to time dt. That's the definition of the Laplace transform of a function, and in this particular case, little u of t is the unit step. That's just 1 for all time t bigger than 0. So let's use that information. This is now going to be the integral from 0 minus to infinity. We just said what u of t was functionally. As a function of time t, u of t we can just write down as a constant 1. That's what the waveform is for all time that we're integrating with respect to, from 0 minus up to infinity. It's 1. Now we still need to weight that by this complex exponential. And what I don't want you to do now is if somebody says, oh, what's the integral of this e to the minus st, you better be able to do that in the next class if they ask that. What is the integral of e to the minus st? Is that okay? That's why you take the calculus. So you can do these difficult integrations. Okay? Doesn't get any more difficult than that. No, it might, but This now is this minus 1 over s. And remember, we are integrating with respect to t, so s's should remain in our function, but t's should be being eliminated or evaluated for in this particular case. We evaluate at the upper limit, and we subtract the function at the lower limit. Now, if s is bounded, we have e to the minus s infinity. And what's e to the minus infinity? 0. So now we have this is going to be minus 1 over s0 minus, and what is e to the 0? That's 1. We have a couple of negatives, and that's now what our unit step looks like as a function of s, its Laplace transform. So we could say, or we could conclude, the Laplace transform of this unit step, which we are calling capital U of s, is 1 over s. And we may talk, and this is sort of hinting, this is maybe getting ahead of where we're wanting to be now, but just as a precursor to what we might do in the future, is we will start identifying poles and zeros. Have you heard of poles and zeros? This particular signal's Laplace transform has a pole at the value of s that causes the denominator to vanish. The denominator is a pretty trivial polynomial. What value of s causes that denominator to be 0? 0. So you have a pole right at the origin for this function's Laplace transform. And we do not have any finite zeros. The zeros are the values of s that cause your numerator to vanish. And there are no finite values of s that cause that Laplace transform to become 0. So we have no finite zeros, and we have one pole at the origin. Let's now look at another example of a signal that we want to Laplace transform. Let's not take too big of a step. No pun intended. Actually, this is going to be a delayed step. So if you were following along, that step that I just took was delayed. Sorry, you're still sleeping and not watching. Here is a way to write or parameterize a delayed unit step. If we keep this t0, t0 is a constant, let's make it bigger than 0. If I now said, okay, sketch this waveform as a function of time, what would you draw? Okay, the unit step hasn't changed any. We've just created a variation on the unit step. The unit step turns on for all values of time where this argument is 0, or non-negative, I should say, where it's bigger than 0. This function then will be 1 as long as the argument is non-negative, as long as t minus t0 is bigger than 0, bigger than or equal to 0. And that's going to be the case as long as we are above or at t0. That's supposed to be a flat line, okay, but I don't like to talk about flat line. So I guess I don't draw them very well. But you can make a better sketch of your delayed unit step. Let's now integrate this to find we now are integrating by definition over time from 0 minus to infinity. Our waveform that we are computing its Laplace transform of is u of t minus t0. we weight that by this complex exponential and integrate over time. Now, the last integral was pretty easy. The only thing now we need to do is make sure that we are, well, what would make this one easier is if we just had u of t in there. Now we have a u of t minus t naught. And one way we can make it look more like what we just had is to introduce some new variables. For example, suppose I let tau be t minus t naught, because then my u would be u of tau, and that's what I feel good about, because I've just now been able to integrate a u of t. Maybe I can integrate a u of tau. If I let tau equal t minus t naught, what's the derivative of tau, or the differential of tau? T naught, remember, was a fixed quantity. We differentiate that, and it's 0, so d tau is just dt. So whenever we see dt's floating around, we'll simply replace it with d tau. The only other thing that we have to worry about is now we need to integrate with respect to tau. So let's get rid of t, and if we look at that definition for tau, we can say that t is related to tau by tau plus t naught, meaning anywhere we see a t, we can replace it with tau plus tau naught. Or we can also use this information when t is equal to 0 minus, what's tau? It's minus t naught. So now we go back to that definition of tau and plug in t equals 0 minus, and we see that tau is equal to minus t naught, meaning if we're integrating from t equals 0 minus to infinity, now we're going to be integrating from tau equal minus t naught up to what happens when we replace t with infinity. Infinity plus something is still infinity. So now we have infinity remaining. We can now use that information to say that if we're Laplace transforming this delayed unit step, we now have this integral from tau equal minus t naught up to infinity of u of tau e to the minus s, but what was t? It's now tau plus t naught d tau. Is everybody okay with what we just did? Now we're integrating with respect to a new variable, tau, instead of t. So now what we're going to do is we're going to use knowledge of these exponents to our advantage. Our variable of integration is tau. S is independent of tau, as is t naught. And we have actually an e to the minus s t naught inside the integral, or in the integrand. Let's factor that outside so that we don't have to worry about it. We now can say that this is the same thing as e to the minus s t naught integral from tau equal minus t naught up to infinity u of tau e to the minus s tau d tau. We okay with that? This is slightly different than what we had before, because before we were integrating from 0 to infinity. This is now a little bit to the left of that. Well, let's not we'll do this in baby steps. Let's say this is e to the minus st. Now we can integrate from tau equal minus t naught up to 0, u of tau e to the minus s tau d tau plus the integral from 0 to infinity u of tau e to the minus s tau d tau. I've simply split my integral into two pieces. But now, the reasoning for that is to make my life easier. I don't want to think too hard. And now what I can do is I can say, what does this unit step functionally equal in these particular integral ranges? We could, well, all we really need, hopefully this right-hand piece looks very warm and fuzzy. That looks just like what we just did in the previous example, doesn't it? So we now know what that's going to be. That's going to end up as 1 over s. The only thing we have to worry about is that left integral. But the left integral, there's a mismatch between the integrand and the limits of integration. The limits of integration are from from tau equal minus t naught to 0. Well, u of t is equal to what over that integral, or interval? 0. Well, that's going to help us. Meaning we can now say that this is the same as integrating from tau equal minus t naught to 0 of 0 e to the minus s tau d tau plus, and this now is this integral from 0 to infinity of 1 e to the minus s tau d tau. And I will try to consistently make my s's a lowercase script s because my printed s might look like a 5. And you'll go, is this s plus 2 or is it 5 plus 2? And there's a big difference between an s plus 2 and a 5 plus 2. If that makes any sense. If it doesn't, don't worry about it. You're probably not going to miss anything. This now is 0. Since we have 0 in our integrand, that integrates to 0. And we're left then with this integral e to the minus s t naught. This is now minus 1 over s e to the minus s tau from tau equals 0 to infinity. E to the minus s t naught. This is now the minus 1 over s 0 minus 1 beast. Or this is now e to the minus s t naught over s. That is the Laplace transform of this delayed unit step. And how does that differ from the undelayed unit step? It has this factor e to the minus s t naught associated with it. T naught again is a number. If you delayed it by a second and a half, t naught would be 1.5. So you'd have e to the minus 1.5 s floating around. Now this particular example actually applies in general. If you know the Laplace transform of little f of t, then actually you can conclude that you know the Laplace transform of a delayed version of little f of t. It's just going to be e to the minus s t naught times the Laplace transform of f of t, and that we've been calling capital F of s. And that's a Laplace transform theorem that you will be able to apply if you need it. If you now know that a waveform, a signal, has a certain Laplace transform, and now somebody says, oh, here's a delayed version of that signal, all you have to do to find that delayed signal's Laplace transform is scale it by e to the minus st naught, and you have it. Okay? Now I promised you, so those are some examples of Laplace transforms. Any questions on that? What's the Laplace transform of a unit step? 1 over s. Okay? And a delayed version is simply scaled by this factor e to the minus st naught. Let's look at two very powerful properties that the Laplace transform enjoys. One is homogeneity. Which says that if I scale this time domain waveform f of t, where a is just a constant, meaning that does not depend on time t or f of t. A is just a number or a constant, capital A. Now if I want to find its Laplace transform, what would you guess that Laplace transform was going to be? Exactly the same scaling applied to what we know f of t's Laplace transform is. So that's homogeneity. The other property, so if you have a Laplace transform and you already know what it is, and somebody now scales that waveform in time, you already now know the Laplace transform of that scaled waveform. The other property is superposition. And you know this from circuit analysis. If you applied superposition to a circuit, what are you doing? Or first of all, what do you assume you have in your circuit? That it's linear, and it's probably time varying, but you probably have more than one source. Otherwise, you wouldn't really have to worry about superposition unless you include initial conditions as sources, and we'll learn how to do that. But superposition says, oh, analyze the circuit with this source, and the other source is zeroed, and now analyze the circuit with this other source and everything else zeroed, and let me add them together and get the total circuit response with the various sources. How do we do that in functions or time domain waveforms? Now we say, oh, if we have the Laplace transform of little f sub 1 and the Laplace transform of little f sub 2, then if we want the sum of those Laplace transforms, that's simply going to be f sub 1 of s plus f sub 2 of s. Now you're going, well, that's pretty trivial. Well, those two trivial properties are very powerful. Once you have those properties, homogeneity and superposition, those are linearity properties. They are what allow each of these circuit elements, these R's, L's, and C's, or sources. So now we have circuit elements or sources. Each circuit element or variable can now be transformed separately. And put back together to allow us to really convert differential equations which might arise from a given circuit into algebraic equations in the frequency domain. So now again, this is this time domain, frequency domain connection that the Laplace transform allows us to do. We've looked at the Laplace transform of a waveform, two waveforms actually. Now let's look at an operation and see if we can find what happens when we perform the Laplace transform on an operation. And one of the most frequent operations we have is the derivative. Meaning, what happens when we Laplace transform not f of t, but its derivative? Well, that actually ends up being something fairly straightforward. If you didn't like to differentiate functions or waveforms, now all you have to do in the frequency domain is multiply by an s of the Laplace transform of the original waveform f of t. And you need to account for initial conditions if that particular waveform has a non-zero initial condition. Again, these are one-sided Laplace transforms that we're talking about. Why is that the case? Now let's look at what happens when we Laplace transform the derivative of a time domain waveform f of t. By definition of the Laplace transform, that's now this integral from t equals 0 minus up to infinity of f prime of t scaled or weighted by e to the minus st dt. And now we need to integrate f prime e to the minus st. I can integrate f e to the minus st because I can just call that capital F of s by definition. So now I want to get to that point. I want to convert this into an integral that just involves f with this scaling factor, e to the minus st. And how did you do that in calculus? How did you lower the derivative order inside your integrand? So now if we integrate by parts, this was what you wanted to do. You knew that when you woke up this morning you were going to do something exciting. Some of you haven't yet woken up, right? But hopefully we will now integrate by parts, and you can remind me how to do that. Let's now put this together. Oh, and you probably use different variables. I'm going to use v and w. So I'm going to say, okay, let v equal e to the minus st. And now what I need to define as dw is what's left over in my integrand when I get rid of, or when I define e to the minus st as v. So my dw is what's left over, and that's this f prime of t dt. And you've already integrated v, so it shouldn't be too hard to differentiate v. What's that? Minus s e to the minus s dt, because we wanted the differential. And now we want to integrate f prime. Well, that's just by definition of what the derivative is. Now we want the antiderivative. So there's our f of t. We started with v dw. Now we're going to get that equal to, by parts, vw minus the integral of w dv, right? So this now becomes what we need. We want to now say that the Laplace transform of f prime of t, which in terms of what we have is this integral of v dw, that's now going to be equal to w, which is f of t, v e to the minus st, evaluated at t equals 0 minus and infinity. So that's our wv piece, and then we subtract from that this integral from 0 minus to infinity of w f of t minus s e to the minus st dt. And that's my w dv. That's my integration by parts. Let me now try to evaluate that. And remember, what I'm integrating with respect to? I'm integrating with respect to time, meaning this s in the square brackets on the right-hand integral, I can just factor that outside the integral. And I have a minus, and that will give me a plus. So let me put these pieces together, hopefully. I now can say that I have f of infinity, e to the minus s infinity, that's the upper limit on the first piece, minus f of 0 minus e to the minus s 0 minus, plus s integral f of t e to the minus st dt from t equals 0 minus to infinity. We're going to assume that f is well behaved, so f of infinity is bounded. That's what I mean by a function being well behaved, that its behavior at infinity is not unbounded. This piece, e to the minus s infinity, dominates that, and so it drives the whole piece to 0. This you've already told me is 1. And what does this look like? That should look like what we've just defined in the first part of the lecture. That's, by definition, the Laplace transform of f of t, little f of t, without the s in front. And if I pull all of those pieces together, I now can say that I have minus f of 0 minus plus s f of s. And that's what I actually wanted to show. Therefore, I can conclude that if I have this derivative, and I take its Laplace transform, and if I know the Laplace transform of little f, then I can find the Laplace transform of f prime. That's just s times f of s minus f of 0 minus. And this, what is that 0 minus? That's time t equals 0 minus. You're evaluating the function of time, f of t, at t equal to 0 minus. That will be a number. So don't think that that's s, or a value of s. This is t equals 0 minus. That's the initial condition on that function f of t. Questions on that? Yes? Well, the question was, can you do this with sines and cosines since they're not really well behaved at infinity? And I would argue or just comment that yes, they are fairly well behaved. They're bounded. If you're trying to find a limiting value, then you would have a problem. It doesn't go to a limit, does it? It just bounces, bounces, bounces. But what are you doing? You're really hitting it hard with an exponentially damped weighting function, e to the minus a huge number. So that e to the minus, nothing's huge anymore with our national debt, but I was going to say trillion or something, but that's not even that big because you have to pay it off. I'll be dead before, anyway. So we have e to the minus a big number that's scaling this bouncing around sine and cosine, and that bouncing around sine and cosine is fairly well behaved relative to this huge decaying term that is scaling it. So it is going to 0. I'm sorry? What isn't well behaved? Something that's not well behaved would be something that grows faster than exponentially. I was going to say you guys are all well behaved, so I can't use you as an example. So I can't put a picture of one of you on there and say this character is not well behaved. But this not well behaved would be something like e to the t squared. That's growing faster than exponentially. Okay? That's not well behaved, and we won't be worrying about signals like that. Something, well, okay. Does that help? So that's the mug shot you want to think of, or one example of something that's not well behaved. Yes, it has to be some, well, you could have exponential increase, and that's actually well behaved because we can always find a number larger than that we can scale by a minus and actually make that dominate the growing exponential. That's why that e to the minus st is in our integrand, so that we can actually use that to our advantage. Now, where was I? Mugshot. No, that's not in my notes. Let's look at an example. But that's one example of a non-well-behaved waveform. Let's look at the following. Suppose somebody says, oh, here's a second-order differential equation. X double prime plus 3x prime plus 2x equal v of t. What? So now if you wanted to go home and impress your roommate or your parents or something, you could say this is what? It's a linear, constant coefficient, time invariant. So you have all sorts of these adjectives that you can throw around. This equation is a linear time invariant, and you might see this as an LTI, linear time invariant. It's time invariant because the coefficients are not functions of time. And it's linear in that if you applied V1 to this, you could get a solution X1. You applied V2 to this, and you'd get a solution X2. Then if you applied alpha V1 plus alpha V2 to this, you would get alpha X1 plus alpha, whatever I said. Did I say the wrong alphas? Anyway, if you get an alpha X1 plus a beta X2 as the output or result. This equation is a linear, time invariant, differential equation. We want to Laplace transform that. This is now in the time domain. And we would have to go into Math 254 and solve this right now if we wanted to solve it in the time domain. And that's possible. But what we want to do is now take it into the frequency domain and do some algebra. We kind of liked our algebra teacher, so we remembered our algebra, right? Calculus is a different, no, I'm sorry. You loved your calculus teacher too, right? Let's now Laplace transform this. We can now Laplace transform. Oh, I didn't define what prime was. X prime is the first derivative. X double prime is the second derivative. Is that okay, notation-wise? And we know by linearity that that's the Laplace transform of the right-hand side, which is v of t. And these two properties allow us to actually say, oh, I can break this up. I just need to Laplace transform the first one, which is the second derivative of x. Then I can scale the Laplace transform of x prime, and I can scale the Laplace transform of x, and that's going to equal, by definition of what I'm saying the Laplace transform of a function is, it's just its capital of s. Is that everyone okay with that? Now I simply need to Laplace transform these waveforms on the left, because I want to take them into the frequency domain. So if I now Laplace transform this, oh gosh, what in the world is that? Well, I know the first step. I know how to Laplace transform a derivative. I just derived that. So, and this is what? This is the derivative of a derivative. So I can at least Laplace transform part of it. I'll just do it twice, won't I? But I'll do it in a couple of steps so that you see what's going on. If I now took the Laplace transform of a second derivative, that's now s times the Laplace transform of x prime. I reduce the order of the derivative by 1, minus, what do I subtract? Is everybody comfortable with that? Because the Laplace transform of a derivative was s times the Laplace transform of that f of t, which was capital F of s, minus what that waveform was, f, not differentiated, but what it was, f at 0 minus. So now we want to reduce the derivative by 1, and that gives us f prime, and we look at what the derivative is doing at 0 minus. All right, this is color-coded. So now get out your 4 different pencils and start writing in color. What's the Laplace transform of 3L of x prime? Everything is scaled by 3. And I have s, x of s, minus x of 0 minus. Is that okay? And finally, I need to Laplace transform this, which is now just plus 2 x of s equaling v of s. And I'm almost done, except now I have to apply that one more Laplace transform expression to get rid of that script L. I want to end up with all capital X of S's and constants and S's and V of S, capital V of S. So if I now replace or continue, I now want to Laplace transform x prime, which was S capital X of S minus x of 0 minus x prime of 0 minus. I can't throw anything away. Is that okay? And so what I'm ending up with is s times s, or an s squared, which hopefully makes sense because I started with a second derivative. So if I started with a third derivative, I would end up with an s cubed. Now I just need to write down, well, I can write it down a little bit differently. I have 3s x of s minus 3x of 0 minus plus 2x of s equaling v of s. And if I now put all of that together, I should end up with, and if I collect terms, so let me now collect terms. What is scaling capital X of S? I have an s squared, I have a plus 3s, and I have a plus 2. All of those coefficients multiply capital X of S. So that gets that piece, and that piece. And then I have some constant pieces. I have a s times a minus x of 0 minus, where that x was a lowercase. I have actually another x of 0 minus, don't I? So now what do I want to do? Well, I can say that I have a minus s plus 3 x of 0 minus. That gets rid of this one and that one. And I then have a minus x prime of 0 minus, and all of that should equal v of s. Did I lose anything? And yes, question. The question is concerning what happened when we Laplace transformed the second derivative. I started in the first step saying, let me just Laplace transform the derivative of x prime. And that's the second derivative. So that's the way to maybe think about it. I want to now Laplace transform the derivative of x prime. So x prime is a new function, so to speak. If that's the case, then I need to multiply the Laplace transform of x prime by s and subtract the initial value of x prime at t equals 0 minus. Does that make sense? Does that answer your question? Any other questions? What are we wanting to do? Well, we probably can't always live in the frequency domain. We need to come back to the time domain, and to do that, we need to find out what little x of t is, because that's what we want. We want our solution of the differential equation. The input was v of t. X of t was the output, but it was governed by this differential equation. We now have a way of solving for capital X of s. If I divide all of the terms by this coefficient, this polynomial in S that scales capital X of S, I can solve for capital X of S. Capital X of S ends up being S plus 3 x of 0 minus plus x prime of 0 minus all over s squared plus 3s plus 2 plus v of s divided by s squared plus the same polynomial in s squared plus 3s plus 2. Questions on where that came from? We can now do algebra with the polynomials in S. The nice thing about the one-sided Laplace transform, and what did it mean to be one-sided? Did everybody get that? That sounded so clear. We've defined a point in the sand, haven't we? We've drawn the point where t is equal to 0, and we're only worried about non-negative time. That's the one-sided Laplace transform. And because we are doing that, the one-sided Laplace transform is unique. We don't need to worry about a region of convergence, if you've heard about that. We won't get into that necessarily here in this class. The one-sided Laplace transform is unique, which means that we can invert it. We can inverse Laplace transform capital X of S to obtain little x of t. So if somebody gives us capital X of S we can find little x of t. And I think you can anticipate how we will denote that. We will now say the inverse Laplace transform of capital X of S will be called little x of t. And from our example, what do we now know? Well, we now know that x of t, little x of t, is the inverse Laplace transform of capital X of S. But capital X of S we actually wrote in two pieces. So we can break this into two pieces. We have the inverse Laplace transform of S plus 3 times x of 0 minus. X of 0 minus is just the initial condition on x at 0, plus x prime of 0 minus all over s squared plus 3s plus 2 plus the inverse Laplace transform of 1 over s squared plus 3s plus 2 times v of s. And the nice thing about this is what is making up the numerator in that expression in blue? What are those little x's? Those are constants. Those are initial conditions. That first inverse Laplace transform is going to be the response of our solution, x of t, due only to initial conditions. So whatever our circuit was with the initial conditions, now we know what the response of that circuit to those initial conditions becomes. This is now the response due to initial conditions. And because of the linearity properties of the Laplace transform, we could actually find those independent of this one, which this piece is going to be the response due to our excitation source. V of t was just the input. That's how we're exciting the system. whether we're driving it with a sine wave, a cosine wave, an exponentially damped sine or cosine. This is now in red, the response. Due to the excitation function. Now, let me give you a quiz. Here's your in-class participation. What I want you to do, since this previous discussion was all related to solving a second-order differential equation, what I want you to do is remind yourself where that differential equation might have come from. I want you to find the governing differential equation for this RLC circuit. Suppose this is now your input V of t. This is L, this is R, and this is C. And you can work together if you want. If you want to. All right, I want the answers to all look somewhat alike, so why don't you write your equations in terms of that capacitor voltage, V sub C of t. Oh, that makes it a lot easier. Continue. So I want R's, L's, and C's, V sub C of t, and V of t in your answer. Okay, you can ask your neighbor, but you can't go onto Facebook and ask your friend. Or find it on the web. Yes, please, put it in standard form. And if you have extra time, you can put it in state space representation. We're going to get there. Okay? We are going to get there. All right, let's just talk about this because I know you're going to go home and start really working this and find the solution for generic V of t's. Let's just think a little bit more about this. If I gave you that circuit and somebody said, okay, does this circuit contain any energy storage devices? Yes. How many what are the energy storage devices? Capacitor and an inductor. So I have two unique energy storage devices, and that actually tells me quite a bit. That tells me now that I should be expecting what order of a differential equation? Second order. So you should be looking for a second order differential equation, which means if you wrote it in terms of the capacitor voltage V sub c of t, you should be looking at second derivative of V sub c and maybe a first derivative and maybe V sub c equaling a V of t. Is that making sense? Now, how would we go about doing that? So we have two energy storage devices. Here are our thoughts. We have two So now we should expect a second order differential equation which might look something like alpha 1 V sub c double prime of t plus an alpha 2 V sub c of t prime plus an alpha 3 V sub c of t equaling, let's say, beta V of t. And what do the alphas and the beta include? The L's, the R's, and the C's. Okay? So that's what we should have maybe ended up with. Now, how do we get there? Or what we are going to do is we will initially solve this in the time domain. Find the differential equations, the governing differential equations, because we now know, based on today's lecture, how to convert those differential equations into the frequency domain and inverse Laplace transform and obtain the answer. We will, subsequent to that, learn how to take this time domain circuit directly into the frequency domain and use frequency domain techniques, which include algebra, to find the solution in the frequency domain, or at least an expression for capital V sub c of t. Make sure and hand in your in-class participation. I want to see where you made it to, and we'll pick up at this point on Tuesday. Yes?